Hey everyone, I am Mohammad Reza Musai and I am presenting our work on detection of deformable linear objects and the physical interaction of aerial robots with these objects. Deformable objects such as cables and wires are part of many of our everyday and industrial tasks. We collectively name them deformable linear objects or DLOs. In order to automate tasks involving DLOs, such as manipulation of cables in industrial settings, utility pole maintenance using UAVs, or stitching with surgical robots, a crucial part is to detect the DLOs in a way that the detection result can be used for further manipulation or planning. On the other hand, to extend the DLO applications to aerial robots, we need to study the requirements for physical interaction of aerial manipulators with DLOs. Some of the challenges in this application that a detection method needs to address includes partial views and occlusions, crossings, existence of multiple DLOs in the frame, and supporting different image types. Finally, the detection method needs to output a model that is suitable for other automation tasks, such as manipulation and planning. While there are many methods for segmentation of DLOs, their output as a collection of pixels is not suitable for most robotic tasks. On the other hand, various tracking methods for DLOs exists that can track the motion of a DLO across the camera frame once it is initialized in the first frame. However, as far as we know, our detection method is one of the few solutions that can fill the gap between the segmentation and tracking methods for robotics purposes. To go through our approach, first, the method segments the input frame. This output has many gaps which needs to be filled and many crossings that needs to be resolved before it can be used. In addition, the segmentation is purely a collection of image points, and we need to model the DLO in a more suitable way. The next step is thinning or skeletization, which allows an efficient extraction of contours in the next step. Each of these extracted contours are used for fitting a small DLO segment, and then all overlapping segments are removed. Finally, we iteratively find two DLO segments that are best fits and connect them together using a computed curve. The final output is a single DLO represented by a sequence of short fixed lengths cylinders connected to each other using a spherical joint. This output can be used as the initial state for tracking methods and had been used in our work for cable routing and manipulation. The whole process is near real time. In these experiments, you can see how the detection and method can handle occlusions and crossings. To extend the physical interaction of DLOs to aerial robots, we analyze the visibility of the tasks from the end effector position perspective in simulation. We also analyzed the required forces for normal everyday manipulation tasks, such as pulling a USB cable, and concluded that even for simpler tasks such as this, the remaining wrenches to perform the tasks are barely enough. With that, I'm going to conclude this talk, and thank you for listening.